All right, okay. I guess what we would like to have right now is like a panel discussion. I'm going to ask some questions about your experience, but also some maybe technical questions. At the same time, so I'll start, all right, I have like one question to start with. At the same time, I will ask you to think also about some questions. So you can ask any of the panel member to answer that question. So maybe let's start with Andrea. You just gave a talk. So Andrea, you're working on one of the emerging fields. And I've seen that the circuit design, and particularly cryogenic circuit design for quantum computer, expanded over past few years, okay, from basically no papers on that, I mean, like, to a large number of papers. So what actually attracted you to this particular kind of field of study, and what do you find most exciting about it? So kind of your personal way, I mean, like, towards circuits for, CMOS circuits for quantum computing.
Yeah, so for me, I think, as probably you could see from my biography, I did a bachelor degree in engineering physics. And I always liked, let's say, to be at the interface between electronics and physics. And I was very fascinated by quantum, even from high school or so. And then during my bachelor, I got really excited about this topic. And then during my master, I studied more about integrated circuit design at EPFL. And this is where basically I fell in love with RFIC design. And then I learned that I could apply RFIC design to the world of quantum, because this was one of the skills in need in that field. And so I think this is a field that I'm really excited about, because it's an emerging one, and I can be a circuit designer, but I can also be a researcher, which is something that is very important for me. I get to explore new designs, I get to invent new circuits, I get to even conceive topologies that might not be used elsewhere because of the stringent requirements that come from quantum, to push you to design new circuits and come up with something new that maybe even exploits the advantages or mitigates the disadvantages of cryogenic operation. So this is how I got, interested in this, by trying to lie at the interface between electronics and physics. And this is what has kept me in this field so far, because I get to experience the innovation. And also, going back to my final point, I get to do innovation, but I get to do research and science, which is also very exciting for me.
Thank you. And maybe just like a second question, so kind of to follow up. So cryogenic CMOS design basically has no industry standard at the moment, as was mentioned. So there are no standard models, PDK models, and so on. So designing circuits and kind of working again with the industry, like with the, let's say, on a task, okay, with no industry standard, I understand you like the creativity, but do you see actually any drawback or limitation or constraint? I mean, like, is there a negative side to that, or it's kind of only positive?
So for sure, at the moment, there is no defined industry standard for quantum, both, as we were touching upon before, in terms of cryogenic device models for circuit design, which in the end are very important for the circuit designer, because that's how you simulate your circuits during the design phase. But also in terms of defining standards, for example, for control or readouts, as you have in wireless. For example, in wireless, there are standards that define the bands and the bandwidth and all the frequencies. I think at the moment, for me, this is a source of creativity, so that you can come up with solutions to find the optimal answers to the problems that we are facing. But I do see that in the future, most likely there will be needs to establish common standards, for example, to say control qubits at a given frequency and read them out at another given frequency, also to standardize and help the industry scale to a level where not everything is possibly done by a single party, but maybe circuit design is handled by some organization, and then the quantum hardware is handled by other organizations. So there will be needs, as there are in wireline or wireless circuits, to establish standards. I don't think we're there yet, but I do see that in the future this might be the case.
Thank you. Okay, so meanwhile, maybe there are some questions from the audience. All right, okay, let's continue then. Javier, as far as I know, you have a lot of experience managing different teams and kind of R&D teams and so on. So I'm pretty sure you actually have encountered some projects with also no well-defined industry standards. So what would be your approach? I mean, so how would you handle, let's say, early career stage engineers working on this, and then also actually maybe, I don't know, established researchers in this field?
Okay, you miss saying despite my youthness. Sorry, just joking. Yeah, definitely. I mean, we're talking about the standards. The standards are critical for industry. Okay, they are important for the dissemination or the success of a product or a technology. But it's very important also to launch the standards in the right moment, because otherwise they can kill innovation. And there are situations where, let's say, there's still too much activity or too many changes, and we have to be careful about when really we need to launch standards. I mean, I tend to prefer to work in these areas where standards are not defined, so you have kind of a blank sheet of paper, and you can enjoy, as Andrea was mentioning, you can really enjoy the research part of it, and let's say add your, let's say, attack the problem from any possible side and try to find the best solution, combining activities from other teams. I love having teams with very diverse views, if it's possible, geographically diverse, with different education, because I think that that's the best way to find the most optimum solution to things. I'm not, let's say, a standard IC designer, so I'm not, let's say, particularly good at, let's say, doing something in the shortest possible time with the shortest cost and exactly the lowest power for something that follows on a standard, and you are going to be 2 cents cheaper than your competitor and win the market. That's not the area I enjoy more. I have done it, but that's not really what drives me and makes me enjoy.
Okay, thank you. Now I have a question for Sarah. So how do we design sensors for the future? So what are the elements that need to be considered when we are designing and manufacturing a sustainable product?
Thank you, Elena. So I did introduce a little bit the concept of sustainability during my talk. We also saw Javier, like how much important it is today to think about sustainability from a power perspective, but we also need to think about sustainability in terms of people. Designing sensors, it's not purely just making, your circuit or your little, module and so on. It's also about ensuring that you have continuation of people coming into the industry, and also continuing developing the skills of your people, making sure that people are always up to date, and also start tapping into those less represented minorities, whether it's women in the population or people from what we consider minorities in the industry today. And I think it's very, very important that the companies start really understanding the importance of doing this. And for me, this is where the future lies. Thank you, Lina.
Thank you. Let me check. Okay, maybe there are questions in the room. Still no. Okay.
No.
All right. Okay. Mahmoud, then a question for you. So you've mentioned this in your talk, so there are new technologies on the horizon, all right? So in particular, we are talking about gate-all-around devices, 3D integration, and so on. So in your opinion, how these are going to change the hardware landscape?
Yeah, I think it's a very exciting time because Moore's law is slowing down. I think this has been mentioned several times in this event. Actually, it had slowed down almost to a halt. And I mean, these 3D integration techniques, new transistors, backside power, they are all tools to the circuit designer, and it's just the leaves it to your innovative mind to take advantage of them. There's of course cost aspect of all of these. The advanced technologies will be more expensive. So I guess incremental gain in terms of performance or energy efficiency you are getting should make sense, so that you are paying extra for the newer technologies you are getting. So for certain market segments, maybe more mature segments, it might not make sense. So you might not see the penetration of these new technologies in those market segments very quickly. But along the way, I think it's going to change the way we are thinking about circuit design. Starting with the like CAD tools, right? Like when you are stacking things in 3D, do you think about each chip as a separate entity and then combine things together, or can you think about ways to partition things into separate die, and which can increase the possibilities in your design, but then I don't think CAD tools are nearly there to support like that type of complexity. So I think it's a very exciting time, again, as I said, and these new technologies will definitely help us explore new frontiers, and then push the envelope of energy efficiency or performance even higher. Yeah, I think as young engineers I see in this room, I think you are going to have not just think about a single die or maybe the classical transistor model, but some things that are more complex. But I think it just is going to be quite exciting. Yeah.
Thank you. So let me check. Still no questions. All right. Okay. Okay. Maybe we'll just maybe I don't know, Ali, as the organizer of the event, you said you actually have many questions for the panel. Maybe we can hear one.
Yeah, I have many questions. So as you remember, I talked about intuition, and I was thinking that when Andrea was giving a talk about quantum states and how we can control them, we understand that quantum concepts are not intuitive. It's just that we don't sense the same way as elements of the nature, such as electrons, behave in quantum state. But I do understand that we probably have an intuition for how to control them, because we're still dealing with circuits. So thank God we have circuits that are essentially working with electrons. But I guess I have two questions maybe that is relevant here. One is that when we're dealing with electronics, we are using electrons to control other electrons, and that is what we're doing. But essentially, we're doing it by the numbers. When we want to have a voltage of certain value, we just bombard that capacitor with 100,000 electrons, and then you have a voltage that you need. So we only deal with numbers. But when we go to the quantum field, we have single electron, and we're trying to take the spin of that electron and move it around. And then, of course, when you go to entanglement, things become super complicated. But I wonder if there is an intuition that you have developed over years for how to understand the behavior of electrons at the quantum level. Is that actually doable, or is that just beyond us at this point?
So I think, let's say, since we're speaking about the electrons, probably the best analogy is referring to spin qubits. In spin qubits, fundamentally speaking, you create some nanometric structures, which are quantum dots, where you try to trap single electrons. And then, roughly speaking, in the simplest way, you typically, let's say, apply a magnetic field which splits the energy levels so that you can identify a two-level subspace. And then the spin of this electron plays a role in defining the quantum state. And then entanglement, as Ali said, is a difficult concept because it doesn't have a classical counterpart. But the way you can think about it, for example, is that electrons, they're particles, but they can also behave as waves in the sense that they have a wave function. And entanglement is realized by typically there is a tunnel barrier. By controlling the height of this tunnel barrier, the wave function of two neighboring electrons can overlap with each other more or less. And this is what determines the degree of entanglement. So this is how you can visualize in your mind and have an intuition about how entanglement works and why you can realize it by controlling single electrons and by basically tuning a voltage which sets this tunnel barrier between them.
Yeah, thank you. So I believe that there are intuitions in development as we move more into this field. Maybe one follow-up question is that in the world of electronics, classical electronics, as we know, we have the concept of controlling the gate with voltage, which electrons, right? And then we can see the impact in the drain current. So essentially, we're controlling the movement of other electrons with other electrons, right? So what I mean by these two others is that one is electrons that we have at the gate, but we have different set of electrons at the drain, and we control the movement of one set of electrons with the movement of another set of electrons. But what is fascinating to me, and please tell me if my understanding is wrong, is that in the world of quantum computation, you're dealing with one electron and you keep working on one electron. It's the same one. You never replicate it on the other side that you will take control of it. You just have one and you keep changing the spin, moving it according to, if I'm talking about the one qubit operation, you keep working on the single electron until you get the final results. And that is fascinating to me that in one world we're using electrons to control other electrons, and in this world, our viewpoint has to change. We are keep working on one single electron until the end, and at some point we decide, okay, that's enough. Let's see if is that a 1 or a 0. Is that correct?
Well, yes, but it's not. Let's say it's not always the same electron. Again, going to spin qubits. Typically, you have the quantum dot is a small island, and then there are two charge reservoirs. And then typically, single electrons tunnel from the charge reservoirs, which you can imagine as the source and drain of a transistor, to this island in the middle. And then ideally, you want to confine one there. But for example, when you perform readout, you need to convert, typically, this is one scheme, you convert the spin to a charge. And when you convert the spin to a charge, you transfer this electron into an electrometer. So this electron then goes into this electrometer and is then processed in various ways by changing the impedance of some particular structure. So in a way, you do control single electrons, but it's not always the same one. You control a few of them, though, which is much fewer than in conventional classical electronics, though.
I guess what in general is not one electron controlling the other one, is that you keep operation on, let's say if you're talking about 1-bit operation, on the same electron all the way to the end. It's not that, you can replicate. For example, if you need to do what we're doing in electronics, we have buffers. The concept of you have a voltage and then you recreate it. We can't recreate that. We just use the same one. And so this is an interesting aspect of this. Anyways, maybe I can ask another question, because I do have a lot of questions. I don't know why you don't have questions. This is surprising. Oh, okay. Question.
I do have a question, if I understand it correctly. So basically, depending on the spin qubit, the state of the spin of that quantum dot can store different levels of information using a single electron. Then you convert to a charge, and then you can use that charge to store the information or anything else. Is that what I understand it correctly?
Yes, more or less that is correct. So, this was just an example to go to the analogy that Ali was proposing with respect to classical electronics, where you regenerate signals with buffering. Indeed, in quantum, the state is encoded in a physical property that should be maintained and should be kept. Already it's a very fragile state, so you should keep it. You're not going to be able to reproduce it, so you can't copy the state. So this is for sure something that applies to quantum.
So my question, looking at through that vision, is that on classical electronics you can store information like 0 or 1. There are two states. On the quantum side, on the spin qubits, is there a limit of how many states you can store using using the spin state?
Okay, so in that case, in quantum, you have two base states, which is 0 and 1, and then your state is a linear superposition of them, which means that this is one of the properties that doesn't really have a classical counterpart. You have a given probability of reading out a state 0 or a state 1, which is set by the coefficients which are in that linear superposition. And then, okay, this is an analogy which is not completely correct for the sake of the explanation. When you scale and you have n qubits, ideally, you can have a superposition. If all these qubits are connected to each other, you can have a superposition of the 2 to the power of n states that can be encoded across these qubits, and this is where the power of quantum computing can be visually, let's say, identified and represented. So this is the limit in terms of numbers that you can encode.
So each one physically somewhere in between the, let's say, 0 and 1, and when you read it out, you can find out that information.
Yeah, so let me answer this question. It's very good, and I think it helps me with my intuition. So I heard someone said, this is not mine, somebody else, said that the example of a qubit is like a coin that you spin it, right, on, let's say, a surface. As long as the coin is spinning, you can't say if it is head or tail, right? It's got a combination of both. You have a probability, for example, if the coin is fake or whatever, you can say is most likely to become head than tail. But in general, if you have a fair coin, you can have a superposition of head and tail at the same time on this. And unless you stop it, you don't know if it is 1 or 0. Is that a good analogy?
Yes, I think so, because you basically, when you know the state of the qubit when you read it out. So reading it out corresponds to stopping the flipping of the coin, and you can see the outcome.
All right, so not to focus all on future quantum computing, let me take the pressure off Angie a little bit. I'd like to have a question for Stefan. So, Stefan, you mentioned that future 5G got me really, or future 6G, which got me really excited, is that you have 100 gigabit per second, right? And then I was just wondering, and you said, of course, if you have your bandwidths larger than your carrier, you have to worry about the side of those carriers because they will go in different directions. So when you're envisioning 100 gigabit per second, what is the carrier frequency that you're thinking about?
Yeah, my wish, as low as possible. I think that's where we see those terahertz frequencies coming into play. And I would not see 100 gigabits per second in a macro case, right? I would see that as maybe if you have very local in a room, you have XR applications, stuff like that. Short range. No, 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 not at all.
You can't hear me. Okay, now I guess you could. So first of all, you're now saying that 6G, I'm sorry, it was my misunderstanding. I thought 6G is like 5G, it just becomes 6G, just one number up, but I have it in my cell phone, but I cannot use it in my cell phone on the street. And then you said that in 6G, they can target you where you are, which was a bit scary, beaming the signal to you only, and then as you move around, they kind of need to follow you. It's like a gun at your head as you move around. But then, what if somebody comes into the room? What happens is that they still try to find that person is, or just bombard the building with that beam, and then somehow the beam will bounce off the wall and then find me.
If I understand the question correctly now, correct me otherwise. I mean, you have a beam, right? But it's not like you from a macro station will have a pencil beam going through a building. I mean, that's not gonna happen.
But even in local area, if I go to another room here,
Yes.
what would happen in that case? You just bounce it against the walls until they get me?
If possible.
Is that possible actually?
It depends on the frequency, right?
I see.
I mean, penetrating walls, millimeter wave frequency is really a challenge.
I see.
And that's where, I mean, you will have different frequencies depending on where you are. We're talking a lot now about smaller cells, indoor applications as well.
I also understand that you can use millimeter waves to identify cavities in somebody's tooth. Is that correct?
I don't know.
Because they can be very localized, and even though you cannot penetrate that far, you don't need to penetrate much in the tooth, and so you can get really good imaging of what is happening inside the tooth, right?
I haven't thought of that, I must admit.
Any expert on any
No
dentist?
dentist here?
No dentist
No?
here
Okay.
who wants to become a circuit designer?
Then we can continue speculating, maybe.
All right. Other questions for any of us? Yes.
So I have a question for Stefan.
Right.
So according to Shannon's equation, so the capacity depends directly on the density of cells. So why wouldn't we, as cell phone users, just be our own cell? So that way, the capacity would depend directly on the number of users. Why isn't that a thing?
Yeah, that would be great, right? Let me see if I understand your question here. You also need the backbone, right? Typically from a base station, you have some kind of fiber connecting the core network. And everyone can be their cell, but then maybe you need a way to get back to the core network. And you can do that. I mean, you can think of device-to-device communication, right? Where you hop between users, for example. That's been thought of as well. Then you have to say if you accept, right, that other people would use your phone to get to the next phone.
But using satellite communications, wouldn't it be able for us to be our own connection to the network itself?
Yes, but reaching a satellite is not a super easy thing. I mean, you could do it, but you probably need a huge antenna, and it will consume quite a bit of power.
Thank you.
Thanks to all the panel, actually, for your talks today. My first question was for Javier. You mentioned, Javier, that copper plays a big part in the harnessing, that not just the amount we have to put in, but the weight. I've heard of some developments or some companies attempting to use plastic fiber as part of the harnessing. Is that a big thing? Is it happened? Is it slow? Is it real?
You should go to another room, I think, because they were talking about it in another room. It was definitely, that's a technology that has been worked. I mean, it's always the same. I mean, there are very cool technologies, and it's always hard, and especially in automotive, you have to really guarantee safety and robustness and durability. So yes, definitely, it's a very real technique. It's a very, let's say, real competitor, and it might be, let's say, the winner. I mean, there's a standard that has been developed on that, so maybe that's one of the beauties of this industry, that it has been continuous competition, continuous, let's say, ambition to improve things, and different techniques being developed and competing, and then the customers finally deciding which is best, or which technology better matches their interest. So yeah, it's possible that let's say this plastic fiber could be a good alternative for lots of the buses, especially the high bandwidth buses that are in the cars.
I had a second question. It was for Sarah. Just to switch gears, you'd mentioned that they put a diffraction grating on the transmit and the receivers in front of the VCSELs. Do they make any attempt to electrically control the grating to adjust the angle, or it's just a filter?
So at the moment, the technology is simply static. But there are studies on whether you can dynamically change the status, and so the state, and so make it change properties. Yes.
Great, thank you.
Question for Javier and Stefan. So, because I think you both mentioned design complexity. So when we look at the systems, there's an incredible amount of transistors and actual just general complexity there. So, and even I think experienced engineers will have a difficult times keeping up with all the design choices. So what to do, okay, not to be discouraged, okay? I mean, like, are there any techniques, any methods, okay, how to deal with design choices and complexity in circuit design?
Okay. I think it's like playing with Lego when you were a kid, right? You start piece by piece. I think it's always impossible to break down, even if they're very complex designs, to break them apart and start with the subsystems. That's typically what we do. So, yeah.
Another aspect is, again, there are many different areas there. I mean, I have experience, for example, with consumer. Consumer is tough market in the sense that you have very, let's say, limited time to do things. There's going to be a very fast ramp up in production, so you can take, you have to measure the risks that you want to take, and you have to be extremely careful. I mean, when we're talking about high precision converters, I mean, if you need to do 3 tape outs, okay, nobody's excited about it, but that's perfectly okay. You know that that's going to generate revenue later on, so it's not a big issue. But there are markets where you have to be extremely careful about what are the risks, or even have some duplicity in your design, because it's going to be better to spend or let's say sacrifice a little bit your margin, but have the guarantee that the first tape out is going to be successful. And these days, especially with low geometries, it's extremely expensive, the tape out, so you have to be very, very careful. I mean, I think that since I started in analog devices, well, not since I started, because I think we spoke Latin by that time, but in the last years, what has grown more is DV, digital verification or design verification. I mean, that's the discipline that has been growing more than even design, because you want to really be sure that what you're going to run is going to work, or at least very likely, because of the cost and because of the time involved in. I mean, you will see the silicon back in 3 months, and then you start checking it, and then you have lost 6 months.
Just want to comment on this, is that sometimes, you know, you look at design and you think, wow, these guys are putting 1 billion transistors together and this is so complicated. But remember that nobody's going to put even 1,000 transistors together and say, I came up with this. They all go through the level of abstraction. So first you think, what I'm going to do, I'm going to use it for, let's say, communicating my voice over the phone to a certain place. Then there's theory of communication. There is Shannon's theorem, there's modulation theorems. You understand that you need to break it down to the smaller pieces. Then you have your modulator block, you have your amplifier block, and then in amplifier, there's certain designs you could go and find out what amplifier you should use. And then, of course, these blocks are going to interact with each other, but we also found a way that we take care of the interactions. For example, you have two blocks. This was the Thevenin and Norton equivalent theorem that I mentioned. You look back, you see what capacitance, what resistance. You look forward, you put it back, and you simulate, and you understand. And then you put these things together, and it becomes very big. So I would say do not be scared of the scale of things, as long as you have a way of abstracting out the basic concepts, breaking it down into pieces, understand every piece, and then understand how you put them together without breaking the rules. So in other words, it's not that I have 10 blocks, each of them works on its own, therefore if I put them together, they're going to work. You have to look at, for example, as we call loading effect of one block over the other one. But once you do this, I don't think any design is more complicated than designing an amplifier. It's just a different level of abstraction that we have to worry about.
And again, something that it's very interesting is, for example, when you are working with drivers and sensors, actuators, is also the adding the environment in that simulation. Okay, so it's not only your chip has to work controlling a motor, so you have to be reading that thing and managing that thing properly, so you include that. I mean, and that's a very exciting area where you really are not only simulating your IC, but simulating how it works with reality and how it interacts with it. That's a very cool part of the...
Yeah, so and actually the power of simulation is becoming more and more important. I totally agree with Xavier. We used to just tape out chips all the time. Silicon was much cheaper. Monolithic technology, it's kind of affordable for us. But when you go, and it takes only 3 months for, cycle time of silicon. If you start having, double stacked, wafers and so on, it takes 6 months to have the wafers out. So, time to market becomes more complex, more tricky, more, tangible. And so what you do is you do a lot of simulations. And, in my team, for example, we developed internal simulation tools to be able to predict the performance of our devices, in a complete manner. So the full system. So from, what you implant in the silicon all the way to what comes out at the end of your full product. So we are able to have a fully integrated simulation system, including the module design and everything. So it is really a step forward.
Yeah, I just thought I mentioned that even though the technology, the number of transistors are improving and moving on exponentially, nobody expects your brain to improve exponentially. Our brain is the same as it was 10 years ago. It's probably the same as it was 20 years ago. And I don't think our mental capacity has increased much over time. The only thing that has changed is this level of abstraction. So we still think with the same mind, and we could create something far more complicated. But the way to do this is through hierarchy. So we understand one level of abstraction well, then we go down. And of course, if it's very large, one person cannot handle it. That's why we need teams. That's why we need all of you here to move into that direction.
Thank you. Yeah, it's a time, yes, yeah, all right.
So I think this ends the panel discussion, and now we have a quiz and a feedback. So I believe Alina has a link that she will display, and this is going to be a very easy quiz. And please remember, there's no, there is right and wrong answer, but there's no grade associated with this. So as long as you participate, you will all receive certificate of participation. And before we end, I just want to say that please do not leave at the end. Stay here. We'd like to have a picture with you. Thank you.